Every event in your life is ruled by time. Yet, modern physics still cannot agree on what time actually is. Is time an illusion or a fundamental, unyielding reality? If time is fundamental, where did it actually start? And where would it end? Did time begin with the Big Bang, or is that question itself is based on a misunderstanding of what time really is? Why is there only a forward arrow of time? Why do relativity and quantum physics describe time so differently? If traveling to the past may be impossible, why does physics still take the grandfather paradox seriously? Time is physically a measurable aspect of reality, but the way humans naturally perceive it as a universal, steadily flowing river from past to the future may be an illusion. The reality of time is best understood by looking at how different areas of science and philosophy dissect it. Through the Einsteinian view, often associated with the block universe, our understanding of reality was profoundly reshaped by showing that time behaves as a relative dimension rather than an absolute universal constant. Time with space gets intertwined with the three dimensions to form a fourth dimension called spacetime. Within this perspective, there is no single cosmic present. What appears simultaneous for one observer may not appear simultaneous for other. The seemingly obvious distinction between past, present, and future becomes far less absolute than everyday experiences suggest. This relative dimension means the fabric of time physically stretches and compresses under the influence of speed and gravity. A cosmic clock running near light speed, sitting on a massive megaplanet, or frozen at the edge of a black hole will permanently drift from our terrestrial timeline. Even Earth's gravity actively slows our clocks compared to the ones if at all were placed farther from gravitational sources. Rather than revealing a single universal clock, these effects suggest that time itself unfolds differently for different observers. While debates and tensions continue around this picture, the thermodynamic view offers a different insight. Consider the arrow of time, entropy. Often described as a measure of number of possible microscopic arrangements of a system, appears to increase as the universe evolves. Beginning from an extremely low entropy state, the universe has been moving towards increasingly higher entropy configurations. This has led many physicists to propose that the direction we experience as the flow of time may be closely aligned with this increase in entropy. When we explore how quantum physics approaches the question of whether time is fundamental or emergent, we encounter the Wheeler-DeWitt equation, a pioneering attempt to merge quantum mechanics and general relativity into a future theory of quantum gravity. Remarkably, the Wheeler-DeWitt equation describes the universe without an explicit time variable. A hypothesis known as Page-Wootters mechanism takes this idea even further. It suggests that the experience of time may emerge from quantum correlations and entanglement. But how? In a hypothetical description of the universe as a whole, the universe can appear entirely static and timeless. Yet, when one part of the universe is compared against another from within the system itself, time can emerge as a relational property. In this view, what we call time may arise from correlations between quantum systems rather than existing as a fundamental background stage. The different perspectives on time still do not provide a universally accepted answer to what time actually is. For time to be fundamentally real, should it have had a beginning? The Big Bang occurred approximately 13.8 billion years ago, marking the earliest point in our cosmic timeline. But what does this mean for time to start? Was there a time before the Big Bang, or is asking that question as meaningless as asking what direction lies further north than the North Pole? Or, in contrast, does the equation itself suggest that time may be more fundamental than the universe we observe? If time were truly fundamental, then why do the best equations describing the subatomic world treat time differently? One might expect a genuinely fundamental ingredient of reality to appear consistently across all scales. Though the confusion persists, we have gained at least one significant clarification. What we read on our watches and calendars are human made units designed to measure and coordinate physical processes occurring around us. The numbers themselves are merely references that help us to track change, motion, cycles, and events. They do not reveal a universal cosmic clock that simply quantify correlations between physical processes, but to have a local reference point with respect to the closest cosmic changes. At the same time, the concepts of entropy and spacetime have fundamentally altered our intuition. Time is not merely a universal river flowing identically for everyone. The direction in which we experience time appears closely connected to the remarkably low entropy beginnings of our universe. As for traveling into the past and preventing your grandfather from selling his properties, it remains unclear whether backward time travel is logically possible, because the famous grandfather paradox reveals the deep logical challenges such a possibility would face. Any attempt to alter the past event appears to create contradictions with our conventional understandings of cause and effect. Right now, our two greatest theories of physics are still in disagreement over what time truly is. One treats time as part of a dynamic spacetime that responds to gravity and motion. The other typically treats time as a fixed background parameter against which quantum events unfold. And hidden within that disagreement lies a possibility. Everything we associate with aging, history, memory, and the passage of life is inseparable from change. We perceive beginnings because things around us begin. We perceive endings because things around us end. From stars and galaxies to civilizations and human lives, our entire understanding of time is built upon a universe that decays to eternal cooling. A clear final statement about time, therefore, remains inseparable from a clear understanding of the origin and fate of the universe itself. If the universe truly began with the Big Bang, then the origin of time may be framed from that perspective, stretching forward towards a future of increasing entropy and eventual cosmic cooling. But the mystery deepens when we ask a more difficult question. What if the universe itself is not sufficient to explain time? And what if understanding time requires us to go beyond the limits of our current picture of the universe? In this video, we discovered that time may look very different depending on how we choose to describe reality. Through relativity, it becomes intertwined with space. Through thermodynamics, it acquires a direction. Through quantum theory, it may emerge from relationships and correlations. Yet, none of these perspectives has delivered a final answer. The question now becomes more optimized. Is time more fundamental than anything that mediates the universe? Or is time itself an emergent phenomenon that only appears fundamental because of the limits of our understanding? In the upcoming discussions, we'll explore the time beyond the limits of the Big Bang itself, thus to untangle several mysteries into simpler questions. Not merely what happened after the birth of the universe, but whether the concept of before even has any meaning. I, for time being, see two intriguing possibilities. If time is purely relational, emerging from interactions and evolutions of the universe itself, then time may have begun alongside the universe at the Big Bang. But if time is truly fundamental, existing independently of the universe, it questions whether the Big Bang may not represent the absolute beginning of the reality. Instead, it could mark the beginning of only our observable chapter of a much larger story. If that possibility is true, then our current understanding of the universe could be incomplete in ways far more profound than we imagine. We'll explore those possibilities in the next video. Let's seek knowledge, let's innovate to sustain. Nandri, Vanakkam.